In this second half of the solutions chapter, we'll be talking about how solubility is really a different form of equilibrium. And so because of that, we can have a K value or an equilibrium constant related to the solubility. And that K value is called the solubility product constant. So we'll start by talking about that. We'll then predict whether a precipitate will form or not based on that KSP value. And then we'll look at the solubility of gases as it relates to temperature and pressure, which we mentioned just briefly in the previous lecture. Alright, so let's start off with what is known as the solubility product constant. The solubility product constant is the equilibrium constant for ionic compounds in water. Okay, so when you see this K with the little SP, that's solubility product is what the SP stands for. And it always applies to an ionic compound dissolving in water. So when we write the equation, or the reaction for this, it's always the ionic solid as your only reactant. When this dissolves in water, the water is not reacting. The water is simply acting as an agent to break apart the ionic compound. So you only have your ionic compound as your reactant whenever you're dealing with a KSP. You'll then have the double arrow, which shows that it is an equilibrium situation, and you will break apart this ionic compound into its cation, make sure you include the charge on it, and its anion. And again, you make sure you include the charge on that. If we look at the second example, we have cation and anion, and we have to be sure that we balance. There were 2 chlorines in the original reactant, so we need a 2 as our subscript. Cl2, if you wrote it by itself, is chlorine gas. But that's not what happens when an ionic compound breaks apart in water. It simply breaks into the ions. So if there's more than one of them, we use that as a coefficient. Notice your polyatomic ions stay together when these break apart in water. So then to write the equilibrium expression, if you'll remember from a few chapters ago when we talked about equilibrium, it's products of reactants raised to their coefficient, but we leave out solids and liquids. So we have our products, calcium ion, carbonate ion, raised to their coefficient, there were no coefficients there, over the reactants. But the reactants were a solid, so those are not included. So you can think of it as being a 1 in the denominator, or just there not being a fraction. In a KSP expression, there is never a denominator because we are always dealing with ionic compounds, ionic solids as our reactants. Same thing for lead chloride. We have products raised to their coefficient. We did have a coefficient this time. Over reactants, and again your reactant is a solid, so it's not included there. At the bottom we have a note about the general range for KSP values. They're usually pretty small, but they can be anywhere from 10 to the negative 3 all the way down to 10 to the negative 54. And if you have a KSP value that small, that ionic compound is really not dissolving at all. Alright, let's look at an example problem here. Which of these 2 compounds, they're the ones we just dealt with, calcium carbonate and lead chloride, which is the least soluble in water? Well, the KSP value tells us something about the solubility because it's the amount of products being multiplied together. The more products you have, the more soluble your reactant is. So in which of these do we form more products? Well, the KSP for calcium carbonate is 10 to the negative 9th, which gives you an idea of the amount of your products formed, while the lead chloride is 10 to the negative 5th, okay, which also gives you an idea of the product. So which of these numbers is greater? This 1 times 10 to the negative 5th is greater than 1 times 10 to the negative 9th, so that would lead me to believe that lead chloride is more soluble than calcium carbonate. The question, I read this wrong, is which is the least soluble, and I was reading it as more soluble. So this one with the smaller value means I'm going to have less product. So opposite of what I was saying, although my reasoning was correct, but it asked for the least soluble. So the calcium carbonate must be the least because it has the smaller KSP value. All right, what is solubility? So remember this from the previous lesson. We talked about solubility was the maximum amount that would dissolve. In this case, our solubility is going to be the maximum molar concentration that will dissolve at a given temperature. So our unit for solubility is going to be capital M for molarity. Here we're talking about it in terms of moles. So it's saying for every 1 mole of your lead chloride that dissolves, if you dissolve one of these, you're going to get 1 of those and 2 of those. So therefore, using that reasoning, if you know how much lead you have dissolved, then you could say that was equal to the amount of lead chloride that broke apart. If you know how much chlorine dissolved, because you get 2 chlorines from this reaction, then half that amount would be the amount of original lead chloride that dissolved. So these values, when the solution is saturated, can help us figure out how much lead chloride could dissolve. All right, here's some more example problems. So we know from this example that the solubility product constant, the KSP, okay, when you read those words, you want to think of this term, for lead 2 fluoride is, and then they give us the value, and they give us the temperature. Remember, these things are temperature dependent, so if the temperature goes up, it may become more or less soluble. We want to write a balanced chemical equation first, write the equilibrium expression second, and then the math is going to be to find the maximum molar concentration of the ions and the molar solubility of the solution. Now, one thing to note here, this A and B that they're asking us to do, these are key steps anytime you have a solubility product problem. But only in very generous situations will they actually ask you to do this. They're kind of guiding you through in A and B so that you can solve C. We've got to know that we need to do A and B regardless if they ask us for it, because that's the only way we can get to C. Alright, so let's look now at A and B, writing the balanced chemical equation, and then writing the equilibrium expression. Okay, so we're going to switch screens here. You can see me writing, hopefully. Alright, so the first thing we're trying to do is write the balanced equation. So we have lead 2 fluoride. That's going to be PbF2. The lead has a +2 charge and the fluorine a -1. Anytime we're dealing with a KSP, our only reactant is that solid. And we're going to have an equilibrium situation where we form the ions. So we're going to form lead +2. That charge was given to me in those parentheses. And a fluoride ion, which has a -1. And then we need to balance, so that's 2 fluorides. Okay, there's our balanced equation. Now for our equilibrium expression. That's KSP equals products, Pb +2, that's the concentration, and F minus, raised to its coefficient, over the reactants, but the reactant is a pure solid always in a KSP. So here is our equilibrium expression. Alright, next question says, if we're looking at C, find the maximum molar concentration of the ions in solution and the molar solubility of the solution. Right, so this is still an equilibrium problem. If we think back to our equilibrium chapter, so we're going to use a rice table. All right, when we do that rice table, remember that this is a solid, so it's not involved in the equilibrium. Okay, so we have our reaction, then we have our initial concentrations. This is dissolving in water, and in water, We're going to use deionized water, not water from the tap, so there's no lead in it and there's no fluoride in it. All right, for the change, we're forming these two, so plus x plus 2x, so just x and 2x on our equilibrium lines. All right, so now let's think about our KSP. We know the value for KSP, it was given to us as 3.6 times 10 to the negative 8. And we can say that's equal to, I'm just pulling down here, so lead, so that's our x, and then fluoride, that's our 2x, and it is squared. Our goal here is to find the molar concentration of these ions, so we're looking for these values. Okay, so 3.6 times 10 to the negative 8 equals 4x cubed. You got to remember to square your 2, and then that's x squared, and x makes x cubed. So divide by 4, and then take the cube root. Okay, so I'm going to put that in my calculator. 3.6 negative 8 divided by 4 equals, and then I'm going to use the cube root. Alright, and when I did that, this is the answer that I got for x. Now x is equal to, if we look back up here, that's my lead concentration. So I can say that the lead concentration is 0.0021 molarity, but the fluoride concentration is 2x. So that's going to be 0.0042 molarity. All right. The second part of the question is, what is the molar solubility of the solution? Well, if we look at our coefficients, the lead, fluoride, and the lead have the same coefficient, so that's a 1-to-1 ratio, which means the molar solubility of lead fluoride is equal to the lead. Okay, so that would be 0.0021. Molarity is also the molar solubility of the lead fluoride. So what that means is that this is the concentration of lead fluoride that can dissolve. And when it does, it's going to form that much lead and twice as much fluoride. This molar solubility is how much I could dissolve of the lead fluoride and saturate the solution. Any more than that, and it's going to fall to the bottom. Okay, any less than that, and the solution won't be saturated at that temperature. Okay, here's that information for A, B, and C typed out for you, perhaps a little bit more neatly, and you can kind of follow. They're using S, where I used X. And S, or X, if we're dealing with a solubility product, could be X, depending on what your variable is, that is equal to your molar solubility. So if you have a KSP problem and they ask you for molar solubility, you're looking for X. If they ask you for the concentration of one of your ions, it could be X or 2X or 3X, depending on which ion it is. Right, so that is how we solve KSP problems.